Empty space is not empty. It is a seething, bubbling ocean of pure energy. This is the hidden truth of our universe, and the key to understanding it lies in the wildest behavior reality has to offer: quantum fluctuations. These are the unpredictable pops and fizzles of existence at the tiniest scales, where particles blink in and out of being from nothing. By the end of this journey, you will understand how these invisible tremors hold the answers to our cosmic origins and ultimate fate. We will explore 30 mind-bending theories, from how a microscopic flicker created every galaxy to whether our entire universe is sitting on a cosmic reset button. What do you believe is the most profound question the universe is asking us? The first and perhaps most humbling theory confronts us with a number so wrong, it threatens to unravel everything we think we know. It is called the cosmological constant problem, and it begins with a simple, terrifying calculation. According to our best theories of quantum mechanics, empty space is not empty at all. It is a frenzied sea of virtual particles constantly popping into and out of existence. Every single point in the vacuum of space, according to the math, should be bursting with an unimaginable amount of this latent energy. We call this vacuum energy. Now, when physicists try to add up all this energy from all these quantum fluctuations across the universe, they get a number. And this number is not just a little big, it is catastrophically, universe-endingly enormous. The theoretical prediction suggests that the vacuum energy density should be about 120 orders of magnitude stronger than what we actually observe. To put that in perspective, that is a 1 followed by 120 zeros. It is the difference between the energy contained in a single grain of sand and the energy of the entire observable universe. If the math were correct, this colossal repulsive force would have blown every atom, every star, every galaxy apart in an instant after the Big Bang. The universe would have expanded so violently that not even the simplest structures could have formed. There would be no planets, no life, and certainly no one to wonder about it. Yet here we are in a cosmos that is expanding, yes, but at a relatively gentle, measurable pace. The observed energy of the vacuum, what we call dark energy, is incredibly tiny but not zero. It is just enough to gently push galaxies apart over billions of years. So we are left with a gaping chasm between prediction and reality, a discrepancy so vast it is often called the worst theoretical prediction in the history of science. This is the vacuum catastrophe. It tells us that something fundamental is missing from our picture. Either our understanding of quantum fluctuations is deeply flawed, or there is a miraculous, perfect cancellation happening that we cannot yet see. This glaring error is not an end but a beginning. It is the first clue that the quantum whispers of empty space are hiding a secret far stranger than we ever imagined. This staggering error demands proof. We need to touch the ghost, and in 1948, a Dutch physicist named Hendrik Casimir proposed a way to do exactly that. He imagined a simple, almost elegant experiment. Take two perfectly smooth, uncharged metal plates, place them parallel to each other, extremely close together, inside a perfect vacuum where nothing should exist. According to classical physics, with no air, no light, and no electrical charge, those plates should just sit there, completely still, indifferent to one another. But Casimir, thinking about the quantum sea, predicted something else. He realized that in the empty space between the plates, only certain wavelengths of the quantum fluctuations can fit. It is like trying to fit a vibrating guitar string between two fixed points. Only specific notes or resonances are allowed. Outside the plates, in the wider vacuum, all possible wavelengths can exist. This creates an imbalance. The pressure from the virtual particles popping into existence on the outside of the plates becomes greater than the pressure from the more limited fluctuations happening between them. The result, Casimir calculated, was a net force pushing the two plates together. It was a prediction born directly from the mathematics of quantum fluctuations, a whisper of the vacuum given physical form. For decades, it remained just a brilliant idea on paper. The force was predicted to be incredibly tiny, measurable only when the plates were brought within a distance comparable to the width of a virus. But by the late 1990s, technology caught up with theory. In precise laboratory experiments, scientists finally measured it. They brought those plates infinitesimally close and they saw them move. An invisible hand from empty space itself pulled them together, exactly as Casimir had foreseen. This was not indirect evidence or theoretical inference. This was a direct, repeatable, physical measurement of the vacuum's energy. The Casimir effect is our first real touchstone in this ghostly realm. It proves that the quantum foam is not just a mathematical abstraction. It is a tangible part of reality that exerts a real physical force. It tells us that if we listen closely enough and build instruments delicate enough, we can feel the universe breathing. But if the vacuum can push plates, what else can it do? Could its faint tremors have once roared with the sound of creation itself? That gentle pressure between two metal plates is a whisper from the quantum sea. But rewind the cosmic clock to the first fraction of a second after the Big Bang, and that whisper becomes a deafening roar that shaped everything. This brings us to the third and perhaps most profound theory, the idea that quantum fluctuations are the literal seeds of all cosmic structure. To understand this, we must step into the era of cosmic inflation, a concept that sounds like science fiction but is our best explanation for the universe we see. Picture the newborn universe, smaller than a single atom, yet unimaginably dense and hot. According to the theory, a strange, repulsive energy field, which we call the inflaton field, dominated everything. And for a fleeting moment, this field did something extraordinary. It caused the universe to expand not just quickly, but exponentially, faster than the speed of light, doubling in size over and over again in the tiniest slivers of time. In less than a blink, a subatomic speck became a cosmos larger than our entire observable universe today. Now, here is where the quantum magic happens. Even in that primordial, energy-drenched state, the inflaton field was not perfectly smooth and uniform. It was subject to the same quantum rules that govern our vacuum today. It was fizzing with microscopic fluctuations, tiny, random variations in its energy value. These were the quantum tremors of the infant universe. As inflation happened, as space itself stretched at an unbelievable rate, it did not just stretch the universe. It stretched those tiny, random quantum wrinkles in the inflaton field along with it. A microscopic bump, smaller than a proton, was suddenly inflated to a scale of billions of light years. Think of it like baking a loaf of raisin bread. The dough is the fabric of space, and the raisins are those quantum fluctuations. As the dough rises and expands in the oven, every single raisin moves away from every other raisin. A tiny, random cluster of raisins in the raw dough becomes, after baking, a vast continent-sized pattern. Inflation did exactly that to the quantum noise. When inflation finally ended, that energy in the inflaton field decayed, flooding the universe with the hot plasma of particles and light we associate with the Big Bang. But it left behind an imprint, a fossil. The stretched-out quantum fluctuations in the field became tiny differences in the density of matter and energy across the newborn cosmos. Slightly denser regions where the inflaton field had a tiny peak had a little more gravitational pull. Over the next billions of years, gravity acted on those seeds. It pulled more and more matter toward those slightly denser spots. The overdense regions grew, collapsing under their own weight to form the first clouds of gas, then the first stars, then galaxies and clusters of galaxies. The underdense regions became the vast, empty cosmic voids we see between the galactic filaments. Every galaxy supercluster, every spiral arm, every planet orbiting a distant star can trace its ultimate origin back to those random quantum tremors in the first fleeting moment of time. We are not just living in a universe that has quantum fluctuations. We are living in a universe that is made from them. The largest structures in existence are the magnified ghosts of the smallest events imaginable. This raises an unsettling and beautiful question. If the pattern of galaxies is just inflated quantum noise, then is the entire cosmic web, in some deep sense, random? This cosmic web, born from quantum static, feels vast and three-dimensional. But what if that is an illusion, a magnificent trick of scale? Theory 4 takes us to the very edge of reality, to a concept so radical it suggests our three-dimensional world is a projection from a two-dimensional surface. This is the holographic principle. The idea did not start with the cosmos, but with black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of its hidden information or disorder, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the point of no return. It was as if all the information about everything that ever fell into the black hole was not stored inside its mysterious core, but was painted pixel by pixel on its spherical surface. Later, other physicists like Leonard Susskind and Gerard T. Hooft took this wild idea and ran with it. They proposed that this might not just be a quirk of black holes, but a fundamental property of the universe itself. The holographic principle suggests that all the information needed to describe everything within a given volume of space, every star, every planet, every person, every quantum fluctuation, can be perfectly encoded on the two-dimensional boundary that surrounds it. Our rich three-dimensional reality, with all its depth and texture, could be like a hologram projected from a flat, two-dimensional surface. Think of a credit card hologram. The flat, shiny sticker holds all the data to create a three-dimensional image that seems to float in space. In this cosmic version, the entire universe we experience is that floating image. The real data, the true source code, exists on a distant two-dimensional screen. But where is this cosmic screen? For our observable universe, the most natural candidate is the cosmological horizon, the farthest point from which light has had time to reach us since the Big Bang. It is the ultimate boundary of everything we can ever see. The holographic principle implies that the quantum fluctuations we have been discussing, those fundamental pops and fizzes of existence, are not truly happening everywhere in three-dimensional space. They are happening on that distant spherical horizon. The fluctuations we measure here in our labs and in our telescopes are just a three-dimensional translation of that two-dimensional data. Every event inside our cosmic bubble, every particle interaction, every birth of a star, is determined by the information encoded and vibrating on that far-off surface. This turns our intuition inside out. It means the most fundamental processes in nature are not local events in the space around you. They are reflections of a grand cosmic film playing on the edge of the observable universe. The gentle tug of the Casimir effect, the primordial seeds of galaxies, all of it originates from a dance of information on a surface we will never physically reach. If this is true, then we are not just living in a universe built from quantum noise, we are living inside a projection of it. And if our reality is a hologram, what happens when the projector flickers? Could those same fluctuations that built the cosmos also contain the instructions for its end? If our reality is a holographic projection, then the projector might be running on a loop it can never escape. This leads us to the fifth and perhaps most expansive theory, a vision of reality so vast it makes our entire cosmos feel like a single grain of sand on an endless beach. It is called eternal inflation, and it suggests our universe is not alone, not special, but just one lucky bubble in an infinite, frothing cosmic sea. To understand this, we must return to that moment of primordial inflation, the explosive stretching that planted the seeds of galaxies. The standard story says inflation started, stretched the universe, and then stopped everywhere at once, giving way to the hot Big Bang. But what if it did not stop everywhere? What if, like a pot of water coming to a boil, it only stopped in patches? This is the core of eternal inflation. The inflattened field, that strange energy that drove the expansion, is thought to have a landscape like a rolling hill with valleys of different depths. The high energy state at the top of the hill is what triggers the rapid, exponential expansion of space. Eventually, in any given region, the inflattened field should lose energy, roll down the hill, and settle into a stable valley. When it does this, inflation stops in that region. The energy of the field is released, creating a hot, dense soup of particles, and a new universe, a bubble universe, is born. Our Big Bang would be exactly that event inside our own bubble, but here is where quantum fluctuations change everything. Even as the field is rolling down, it is still subject to those random quantum jitters. In most of the region, it rolls down and inflation ends, but in some tiny, random patches, a quantum fluctuation can kick the inflattened field back up the hill, back to that high energy state. In those patches, inflation does not stop, it reignites and continues at a furious pace. Now, because inflation itself stretches space exponentially, those tiny patches where it continues become enormous, far larger than the bubbles where it stopped. Within these newly inflated regions, the process repeats. Most of it settles down to form new bubble universes, but random quantum fluctuations always create new pockets where inflation roars on forever. The result is a self-replicating, never-ending process. Inflation, overall, never stops. It becomes eternal. It creates an ever-growing fractal of space-time, constantly giving birth to new bubble universes, each pinching off into its own isolated reality. This is the multiverse in its most physical form, an infinite foam of universes, each a separate bubble in an eternally inflating background. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one bubble among an uncountable infinity. And because the inflattened field can settle into different stable valleys, or even different types of fields could be at play in other bubbles, each universe could have different fundamental properties. The strength of gravity, the mass of an electron, the number of spatial dimensions, even the value of the cosmological constant that we find so mysteriously small, could all be different. In some bubbles, the constants might allow for stars and planets and life. In most, they probably would not. In this breathtaking picture, we are not in a fine-tuned universe. We are in a universe that is simply one possibility in an endless lottery. The vacuum catastrophe, the strange smallness of dark energy, might not be a puzzle to solve, but a random ticket we happen to draw. We exist because our bubble's particular laws permit our existence. This idea is both humbling and liberating. It suggests that all of cosmic history, from the first quantum tremor to the rise of civilizations, is a local story in a single bubble. But if our bubble had a beginning, could it also have an end? What happens when a universe grows old and tired? An eternal multiverse of bubbles is one staggering possibility. But to understand how such a thing could even be possible, we must shrink our perspective to the absolute limit, to the very fabric from which those bubbles are blown. This brings us to Theory 6, a journey to the base layer of reality, where spacetime itself loses its smoothness and becomes a churning, chaotic sea. We are talking about spacetime foam. Our best description of the large-scale universe is Einstein's theory of general relativity, which paints spacetime as a smooth, flexible fabric warped by mass and energy. It is a beautiful, continuous geometry. Our best description of the very small is quantum mechanics, which tells us that everything is granular and probabilistic, subject to wild fluctuations. These two theories are the pillars of modern physics, and they work perfectly in their own domains, but they are fundamentally incompatible. They cannot both be correct at the same place and time, specifically at the very smallest possible scale in nature. This scale is known as the Planck length. It is about 1.6 times 10 to the negative 35 meters. That is so small, if you enlarged an atom to the size of the observable universe, the Planck length would be roughly the height of a single tree. At this unimaginable scale, the energy of quantum fluctuations becomes so intense that they do not just affect particles within spacetime, they warp the stage itself. According to the uncertainty principle, there is a fundamental trade-off. In a tiny region of space, for an incredibly brief moment, you can borrow a tremendous amount of energy. At the Planck scale, the borrowed energy is so colossal that it warps gravity itself. This means the smooth geometry of general relativity must break down. Spacetime cannot remain a calm, continuous fabric. Instead, it is theorized to become a seething, probabilistic froth. Picture an ocean in a storm, but instead of water, the very concepts of here and there, before and after, are churned into a bubbling chaos. In this spacetime foam, the structure of reality is not fixed. Microscopic wormholes, tiny bridges connecting different points, are thought to constantly blink into and out of existence. Topology, the very shape of space, might be constantly changing, with tiny handles and tunnels forming and dissolving in a quantum frenzy. This is not empty space with particles in it. This is space itself becoming a boiling, dynamic entity. This foamy picture is not just a wild guess, it represents a critical frontier. Any successful theory of quantum gravity, a theory that unites the large and the small, must explain what happens in this realm. One leading candidate, loop quantum gravity, takes this granularity seriously. It proposes that space itself is not infinitely divisible, but is woven from tiny, discrete loops of gravitational field, a fabric of finite threads. In this view, the smooth spacetime of our everyday experience is an average, an illusion that emerges from the collective behavior of these fundamental quanta, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. The violent fluctuations of the foam are the jittering of these individual threads. The challenge for all such theories is immense. The Planck scale is so far removed from our experiments that testing these ideas directly seems almost impossible. Yet the implications are everywhere. If spacetime is foamy at its heart, then it might leave subtle fingerprints on things that travel across the cosmos like particles of light. A photon traveling for billions of years through this microscopic chaos might have its path very slightly scrambled, like a whisper passing through a turbulent room. Some scientists search for these tiny irregularities in the light from distant gamma-ray bursts. The search for spacetime foam is a search for the grain of the cosmic projector. It asks if the screen upon which our holographic universe is projected is, itself, made of something far stranger and more turbulent than we ever dreamed. That microscopic froth is the chaotic bedrock of reality. But what if your own motion could change the very nature of the quantum sea around you? This brings us to a theory that ties the quantum vacuum directly to the most fundamental sensations of physics, acceleration and heat. It is called the Unruh effect, and it reveals that the vacuum is not the same for everyone. Imagine you are floating in the deepest, darkest, most perfect vacuum of space. You are completely weightless, at rest relative to the cosmic background. According to quantum field theory, you would perceive the vacuum exactly as we have described it, a seething but balanced sea of virtual particles. It would feel empty and cold. Now fire your rockets, you begin to accelerate, moving faster and faster. From your new perspective, something extraordinary happens. The vacuum begins to glow. You would no longer perceive empty space. Instead, you would find yourself immersed in a warm bath of low-energy radiation. It would have a specific temperature directly proportional to your acceleration. the harder you push your engines, the hotter this ghostly glow would become. This is not a trick of your instruments. The Unruh effect, predicted by physicist William Unruh in 1976, states that an accelerating observer will detect particles in a quantum field that an inertial or non-accelerating observer sees as empty. Those virtual particle pairs popping in and out of existence. For the accelerating observer, one member of the pair can appear to become real, giving rise to a detectable thermal spectrum of radiation. It is as if acceleration itself stirs the quantum foam, making its hidden energy perceptible. The key to understanding this is the concept of an event horizon, but not from a black hole. When you accelerate constantly through space, there is a boundary behind you that information from certain regions can never cross to catch up to you. This is called a Reindler horizon. From your accelerating viewpoint, this horizon behaves in a way remarkably similar to a black hole's event horizon. And just as Stephen Hawking showed that black holes should radiate a thermal glow due to quantum effects at their horizons, the Unruh effect shows that an acceleration horizon produces its own thermal radiation. The vacuum state itself is relative. What looks like nothing to one observer looks like a warm particle bath to another, simply because they are moving differently. This is a staggering revelation. It links three seemingly separate concepts, acceleration, heat, and quantum fluctuations, into a single, elegant framework. But the deepest implication is the bridge it builds to gravity. Einstein's great insight, his equivalence principle, tells us that standing still in a gravitational field, like on Earth, is physically indistinguishable from accelerating through empty space in a rocket. If accelerating through a vacuum makes it feel warm, then standing still in a gravitational field should, in principle, do the same. The Unruh effect whispers that gravity itself should have a temperature. This profound hint is a major clue in the quest to unify quantum mechanics and gravity, suggesting that the fabric of spacetime may ultimately be understood as a kind of thermal, statistical property emerging from more fundamental quantum bits. So the next time you feel the steady pull of Earth's gravity holding you in your chair, remember, according to the deepest laws of physics, you are accelerating. And somewhere in the quantum whispers of the space around you, there may be the faintest, undetectable warmth of creation itself. If motion and gravity can heat the vacuum, what happens when gravity becomes infinitely strong at the edge of a black hole? The faint warmth of acceleration is a whisper, but at the edge of a black hole, that whisper becomes a scream that can tear the cosmos apart. This is Hawking radiation, and it is the most dramatic consequence of marrying quantum fluctuations with gravity. For decades, black holes were thought to be the ultimate cosmic vacuums, regions of spacetime where gravity is so intense that nothing, not even light, could escape. They were simple, eternal, and perfectly dark, but in 1974, Stephen Hawking performed a calculation that changed everything. He asked a deceptively simple question. What happens to the quantum vacuum right at the edge of a black hole's event horizon? Remember, the vacuum is not empty. It is a sea of virtual particle pairs constantly blinking into existence, borrowing energy from the universe before annihilating and paying it back. Normally, this happens seamlessly, but Hawking realized that the immense gravitational gradient right at the event horizon could interrupt this delicate dance. Imagine a virtual particle pair popping into existence so close to the edge that one particle appears just outside the horizon, while its partner appears just inside. The particle inside is trapped, doomed to fall into the black hole's singularity. Its partner outside, however, is now free. With its partner gone, it cannot annihilate. The debt of energy borrowed from the vacuum cannot be repaid. This free particle becomes real, carrying positive energy away from the black hole. To balance the cosmic books, the particle that fell in must carry negative energy. And when negative energy falls into a black hole, it reduces the black hole's mass. From the perspective of a distant observer, It looks as if the black hole itself has emitted a particle of radiation. This is Hawking radiation. It is not radiation coming from within the black hole, but radiation created from the twisted quantum vacuum at its very boundary. Hawking's calculations showed this radiation would have a precise thermal spectrum, a perfect blackbody glow with a temperature inversely proportional to the black hole's mass. A stellar mass black hole would have a temperature of only a few millionths of a degree above absolute zero, making its radiation utterly dwarfed by the cosmic microwave background. But for a tiny, hypothetical black hole the mass of a mountain, the temperature would be immense and it would glow brightly. This leads to the most startling conclusion of all. Black holes are not eternal, they slowly evaporate. By emitting Hawking radiation, a black hole loses mass. As it loses mass, its temperature increases, causing it to radiate faster. For a large black hole, this process is unimaginably slow, taking many times the current age of the universe. But eventually, in a theoretical finale, the black hole would shrink until its final moments, where it might vanish in a burst of high-energy radiation. Hawking had connected three great pillars of physics, quantum mechanics, general relativity, and thermodynamics, into a single, beautiful, and terrifying equation. But this triumph created a paradox that threatens the very foundation of reality. The radiation Hawking described is purely thermal, random noise. It contains no information about what fell into the black hole. If a book, a star, or a person falls in, all that unique information is seemingly lost, scrambled into featureless heat. This violates a core principle of quantum mechanics, which states that information must always be preserved, never destroyed. This is the black hole information paradox, a conflict that has driven theoretical physics for 50 years. It asks if the universe, at its most extreme, forgets. The resolution to this paradox may lie in understanding those quantum fluctuations not as a flaw in the vacuum, but as the very language in which the cosmos writes its own history. Hawking's paradox suggests a universe that forgets, but what if the opposite is true? What if every quantum connection is remembered and etched into the structure of reality itself? This leads us to a breathtaking conjecture that reimagines the nature of connection. It is called ER equals EPR, and it proposes that the strangest phenomenon in quantum mechanics and the strangest prediction of general relativity are not just similar, they are literally the same thing. On one side, we have EPR, named for Einstein, Podolsky, and Rosen. In 1935, they highlighted what Einstein famously called spooky action at a distance, quantum entanglement. This is the bizarre link between two particles that have interacted, where measuring the state of one instantly determines the state of the other, no matter how far apart they are. This connection seems to defy locality, the idea that objects are only influenced by their immediate surroundings. It appears as a ghostly, non-physical link across space. On the other side, we have ER, named for Einstein and Rosen. In that same year, 1935, they discovered something else in the equations of general relativity, the Einstein-Rosen bridge, better known today as a wormhole. This is a theoretical tunnel, a shortcut through the fabric of spacetime that connects two distant regions. If you could traverse it, you could travel from one point to another faster than light could travel the normal way through space. But these wormholes, as described by classical physics, are unstable. They would pinch off instantly, making passage impossible. They are like cosmic threads, too fragile to bear any weight. For decades, these two ideas, EPR entanglement and ER wormholes, were seen as completely separate, one belonging to the quantum world and the other to the realm of gravity. But the ER equals EPR conjecture, championed by physicists like Juan Maldacena and Leonard Susskind, boldly claims they are two descriptions of the same underlying reality. Think of it this way: you have two entangled particles, say two electrons with perfectly correlated spins, one here on Earth and one on a planet in a distant galaxy. According to quantum mechanics, they share a single quantum state. The conjecture suggests this abstract mathematical connection has a physical manifestation in the geometry of spacetime. That connection is a microscopic wormhole, a tunnel in the spacetime foam linking the locations of the two particles. This wormhole is not a tunnel you could ever travel through. It is Planck scale, fantastically tiny and transient, flickering in and out of existence with the quantum foam, but it provides a geometric picture for the entanglement. The spooky action is not action through space, it is a connection that uses a shortcut through the fabric of spacetime itself. This idea turns our intuition on its head. We usually think of space as the stage and particles as actors on that stage, connected by forces. ER equals EPR suggests the stage itself is built from the connections between the actors. Entanglement is not happening in space, it is what stitches space together. Every quantum link in the universe might be underwritten by a tiny, fluctuating thread of spacetime geometry. This provides a radical new perspective on the black hole information paradox. Imagine two entangled particles. One falls into a black hole while the other remains outside. According to the conjecture, they are connected by a microscopic wormhole. As the black hole evaporates via Hawking radiation, the information about the infalling particle is not lost. It is transmitted through this wormhole connection to the radiation particles outside, preserving the quantum information. The interior of the black hole and the exterior radiation remain entangled, connected by a complex web of these spacetime threads. The paradox dissolves when we see entanglement and geometry as one. If this is true, then the quantum fluctuations of the vacuum are not just random noise. They are the constant knitting and re-knitting of spacetime itself, weaving the cosmic tapestry from an infinity of tiny, entangled threads. The universe does not forget. It remembers everything in the very shape of its existence. Our reality may be woven from entangled threads, but what if the entire tapestry is an illusion? This brings us to a theory so unsettling it questions the very foundation of experience, the Boltzmann brain paradox. It begins not with cosmology, but with a deep principle from the 19th century, the second law of thermodynamics. This law states that entropy or disorder always increases in a closed system. It is why ice melts in your drink, why perfume spreads through a room, and why we remember the past but not the future. It gives us the arrow of time. In the 1870s, physicist Ludwig Boltzmann sought to explain this law through statistics. He realized that a system is more likely to be in a disordered state simply because there are vastly more ways to be disordered than ordered. A sandcastle is a rare, ordered arrangement of grains. The wind and waves will almost certainly scatter it into the more probable, disordered state of a flat beach. But here is the twist. In a system that fluctuates randomly over an infinite amount of time, even the most extraordinarily unlikely event will eventually happen. Given enough time, a gust of wind could, by pure chance, assemble all those scattered grains back into the shape of a sandcastle. It is astronomically improbable, but in eternity, probability is not a barrier, it is a guarantee. Now apply this logic to the entire cosmos. Our universe is in a remarkably ordered, low-entropy state. We have galaxies, stars, planets, and living beings, all pockets of incredible structure. The standard story is that this order was seeded by the low-entropy conditions of the Big Bang and has been gradually dispersing ever since. But if the universe is eternal and fluctuating, as some models suggest, then over infinite time, random quantum fluctuations could, by sheer accident, assemble anything. And the most disturbing possibility is the spontaneous formation of a fully conscious brain, complete with false memories of an entire life and a universe that never existed. This is a Boltzmann brain. It would pop into existence from the quantum foam, convinced it is a person sitting somewhere watching a video with a lifetime of coherent memories, all fabricated in an instant by a freak statistical fluctuation. From its perspective, everything would seem perfectly normal. It would have memories of childhood, of learning physics, of the apparent order of the cosmos. But its entire reality would be a fleeting, solitary accident in an otherwise vast, empty, and eternal void. The paradox cuts to the core of scientific reasoning. Our entire cosmology is based on observations, the cosmic microwave background, the distribution of galaxies, the laws of physics we have deduced. But if Boltzmann brains are possible, and in an eternal, fluctuating universe they are not just possible but statistically inevitable, then there would be vastly more of these disembodied, hallucinating brains than there are real, evolved observers in an ordered universe like ours. Therefore, if you are a conscious being having observations, you are statistically much more likely to be a random Boltzmann brain than a real person in a real cosmos. This makes our trust in our observations, the very data that tells us about the Big Bang and quantum fluctuations, completely unreliable. Why should we believe any measurement if it is far more probable we are just a momentary glitch? Physicists take this paradox seriously because it is a powerful reductio ad absurdum, a logical tool that shows if your theory predicts something absurd, your theory might be flawed. The existence of real, ordered observers like us is evidence against cosmological models that predict we should almost certainly be Boltzmann brains. It forces us to seek theories where our ordered universe is not a freak accident in an eternal sea of chaos, but a natural, probable outcome. Perhaps our universe had a definite beginning, a Big Bang that set a low entropy starting point, breaking the symmetry of time. Or perhaps we live in a multiverse where new ordered universes are constantly being born, making our existence not a miracle but a common occurrence. The Boltzmann brain paradox is not a claim that we are illusions. It is a warning sign on the road of cosmic theory, a flashing red light telling us that if our map of reality leads to a place where consciousness is more likely to be a lie than a truth, we may need a new map. It asks the most intimate question possible: how can we be sure that our memories and this moment right now are real? The unsettling possibility of being a fleeting illusion forces us to anchor our reality in something tangible, something we can measure. And the most pressing measurement in modern cosmology points to a force that seems to defy both intuition and our earlier theories: the accelerating expansion of the cosmos. We call its source dark energy. For decades, the simplest explanation was that dark energy is the cosmological constant, a fixed property of empty space itself, an unwavering pressure woven into the fabric of the vacuum. That gentle push from the quantum sea stretched thin across the universe, but what if that constancy is an illusion? What if dark energy is not a static feature of space, but a dynamic, changing entity? This is Theory 11, the idea of quintessence. The name comes from the ancient philosophical concept of a fifth element, a celestial substance distinct from earth, air, fire, and water. In cosmology, quintessence proposes that dark energy is not the constant hum of the vacuum, but a quantum field that permeates all of space, much like the inflattened field that drove the Big Bang's inflation. But unlike the inflattened field which decayed long ago, or a cosmological constant which is frozen, the quintessence field is dynamic. It can evolve. It can have peaks and valleys in its energy landscape, and it is subject to its own quantum fluctuations. Imagine it not as a flat, featureless plane, but as a rolling hill covered in a light, shifting mist. The value of the field at any point in space and time determines the strength of the repulsive force we call dark energy. In its early state, the field might have been perched high on a slope, contributing to that initial burst of inflation. Then it could have rolled down into a shallow valley, where its energy became almost negligible for billions of years, allowing matter to clump into galaxies and life to emerge. Now, in the present epoch, it might be settling into a deeper valley, or even just beginning a new, slow roll, causing the accelerated expansion we observe today. The critical difference is that this field can change. Its energy density, and thus the strength of dark energy, could increase or decrease over cosmic time. This turns a simple mystery into a dynamic drama with multiple possible endings for the universe. If the quintessence field continues to grow in strength, the acceleration could become catastrophic. This is the Big Rip scenario. A dynamic dark energy that grows without bound would eventually overcome every force that holds things together. First, galaxy clusters would be torn apart. Then individual galaxies. As the acceleration intensifies, stars would be ripped from their orbits, planets would be shredded from their solar systems. In the final moments, atoms themselves would be torn apart, nuclei separated from electrons, and finally, the very fabric of spacetime might be ripped asunder. It is an end not with a whimper, but with a violent, fundamental disintegration. Conversely, the field could decay. It could roll into a true minimum and vanish, its energy dissipating. If that happened, the acceleration would stop. The universe would settle into a long, slow coast, with gravity once again taking the dominant role. Expansion would continue, but ever more slowly, leading to a cold, dark but stable cosmos, a gradual fading rather than a sudden tear. Or, in a more exotic twist, the field could oscillate. It might bounce between different values, causing the expansion of the universe to alternately speed up and slow down in a cosmic heartbeat over eons. The evidence for any of this is subtle and buried in the most precise observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe. Scientists are searching for any tiny sign that the strength of dark energy has changed over the past few billion years. Finding such a sign would be a revolution, proving that the dominant force in our cosmos is alive, breathing, and fluctuating. It would mean the fate of everything is not yet written in stone, but is instead a story still being told by the restless whispers of a quantum field we are only beginning to sense. Dark energy's potential dynamism is one cosmic mystery, but it is only half the story of the unseen universe. The other half is an even more elusive substance, dark matter, the invisible glue holding galaxies together. For decades, the leading candidate was a class of heavy, sluggish particles moving slowly through the cosmos. But there is another, more ethereal possibility, one that emerges directly from the quantum hum of the early universe. These are the ultralight dark matter candidates, and the most famous among them is a hypothetical particle called the action. The action was not originally invented to explain dark matter. It was proposed in the 1970s to solve a deep puzzle in particle physics known as the strong CP problem, a fine-tuning issue concerning the forces inside atomic nuclei. But physicists soon realized this hypothetical particle had all the right properties to be the missing mass of the cosmos. Unlike the heavy, cannonball-like particles previously imagined, the action would be incredibly light, trillions of times lighter than an electron. And it would not be born in the fiery aftermath of the Big Bang like ordinary matter. Instead, actions are thought to be a product of a cosmic phase transition, a moment when a specific quantum field in the early universe settled into a new state, like water freezing into ice. As that field settled, it began to oscillate, and those oscillations, those ripples, are what we would call actions. In essence, actions are not point-like particles in the traditional sense. They are more like coherent waves, a sea of vibration frozen into the fabric of space, a fossilized quantum fluctuation stretched across the entire cosmos. This wave-like nature changes everything about how dark matter would behave. Imagine the difference between a swarm of bees and a single, vast, vibrating drumhead. The heavy particle model is like the bees, each individual moving independently, clumping together under gravity. Actionic dark matter is like the drumhead, a single, smooth, wave-like entity permeating a galaxy. This could solve some of the lingering puzzles that the heavy particle model struggles with. For instance, simulations predict that galaxies like our Milky Way should have hundreds of small satellite dwarf galaxies orbiting them. We observe only a handful. The wave-like nature of ultralight dark matter, like actions, would suppress the formation of these tiny structures, creating a distribution that better matches our telescopes. Furthermore, because these particles are so light and wave-like, their quantum properties become important on astronomical scales. This could prevent dark matter from cusping too densely at the centers of galaxies, another discrepancy between theory and observation. The action field would be everywhere, a subtle vibration whose collective mass provides the gravitational scaffolding for every star and spiral arm. Detecting such a ghost is a monumental challenge. Since actions are so light and interact so weakly, they would pass through the Earth and our bodies as if we were not even there. But their wave-like quantum nature gives experimenters a unique angle. In powerful magnetic fields, theory suggests, an action could very rarely convert into a faint photon of light. Experiments around the world, like sophisticated radio receivers tuned to listen for this impossible whisper, are searching for this conversion. They are not looking for a particle collision in a traditional sense. They are listening for a specific note in the cosmic static, the hum of a universe filled with a quantum field that froze at the dawn of time. If actions or similar ultralight particles are real, then dark matter is not a collection of hidden rocks. It is a symphony, a vibration set in motion by the first quantum tremors, its silent music holding the shape of the night sky. But if the vacuum can freeze into such a field, what other hidden structures might be woven into the nothingness around us? That silent symphony of dark matter holds the galaxies together, but it cannot answer a more fundamental question. Why is there anything to hold together at all? Why does our universe contain planets, stars, and us, instead of just a featureless bath of light? This is the mystery of matter's existence, and its solution lies in a set of cosmic rules known as the Sakharov conditions. In the first instance after the Big Bang, the universe was a searing, dense plasma of energy. According to our best theories, this energy should have condensed into equal amounts of matter and antimatter. For every proton created, an antiproton should have been born. For every electron, a positron. And when matter meets its antimatter twin, they annihilate in a flash of pure radiation, leaving nothing behind. If the early universe had been perfectly symmetrical, every particle would have found its opposite, and the entire cosmic story would have ended in a silent, eternal glow. There would be no atoms, no chemistry, no possibility for life. Yet here we are in a cosmos made almost entirely of matter. Every object you see, every part of you, is made from the tiny surplus, the 1 in a billion particles of matter that survived the great annihilation. To create this surplus, something had to break the perfect symmetry of creation. In 1967, the Soviet physicist Andrei Sakharov outlined the 3 necessary conditions for this to happen, a recipe for making a universe of stuff. First, the processes governing particle interactions must violate what is called charge conjugation and parity symmetry. This is a mouthful, but it means the laws of physics must treat matter and antimatter slightly differently, providing a tiny bias in favor of one over the other. We have actually observed this violation in certain rare particle decays, but the effect is far too small to account for the universe we see. Second, the universe must have been in a state far from thermal equilibrium. You need a moment of dramatic, rapid change, a cosmic shudder where the rules can be written before things settle down. Think of it like chilling a glass of superheated water. If you cool it slowly, you get a uniform liquid. But if you shock it with a sudden freeze, you get a chaotic, fractured structure of ice. That sudden change, that moment of disequilibrium, is essential. The rapid expansion of the universe during its earliest phases, perhaps even during inflation, provided this dramatic shift. The third condition is the one that ties it all to the quantum sea. Baryon number must be violated. Baryons are particles like protons and neutrons, the heavy building blocks of atoms. For matter to be created from energy, the total number of baryons in the universe must change. It cannot be a conserved quantity like a ledger that must always balance. This is where quantum fluctuations and the wild energies of the early universe come into play. In those first moments, the universe was so energetic that it could have hosted processes we cannot replicate today, events where baryon number was not fixed. Grand unified theories, which attempt to merge the fundamental forces, predict the existence of incredibly heavy particles that decay. Thanks to the first condition, the matter-antimatter asymmetry, these decays could have produced just a few more quarks, the components of protons, than antiquarks. When all the annihilations were finished, those extra quarks were left over, the raw material for everything that followed. The quantum fluctuations in the inflaton or other early fields provided the random seeds, while the violent, out-of-equilibrium conditions of the expanding cosmos amplified that tiny bias into a cosmic legacy. It was a perfect storm of broken symmetry, chaotic change, and quantum chance. So the next time you look at your hand, remember, you are not just made of stardust. You are made of the 1 in a billion, the survivors of the universe's first and most important vote, a decision tipped by a quantum tremor in the fabric of time itself. The universe's matter is a testament to broken symmetry, but the very mechanism that planted its seeds may contain a fatal flaw. This is the trans-Planckian problem, a challenge that strikes at the heart of inflation itself. We have seen how inflation takes a microscopic quantum fluctuation, smaller than a proton, and stretches it to the scale of a galaxy cluster. It is a magnificent idea, but it forces us to ask a disturbing question about the starting point of that process. To create the large-scale structures we see today, the initial quantum fluctuations that inflation magnified must have had wavelengths far, far smaller than the Planck length. The Planck length, you will recall, is that fundamental limit, the scale at which the smooth fabric of spacetime dissolves into a foamy quantum chaos. It is the edge of our known physics, but inflation's mathematics requires those seed fluctuations to originate from scales even tinier than that, from a realm where our theories of quantum fields and general relativity simply do not apply. They are extrapolated from a domain we cannot describe. It is as if we are telling a beautiful, coherent story about how a single whispered word in a cathedral can, through a series of perfect echoes, create a symphony. But then we admit that the original whisper was not a sound at all, but a vibration from a dimension where the very concept of sound has no meaning. The problem is one of consistency. Inflation uses the well-tested rules of quantum field theory, which assumes a smooth classical spacetime as its stage to describe the birth of these fluctuations. But it then uses that same theory to describe processes that occurred when the stage itself, spacetime, was not yet formed or was wildly fluctuating. We are applying a theory beyond its known domain of validity. Proponents of inflation have proposed ways to skirt this issue. Some suggest that new physics at the Planck scale, perhaps from string theory or loop quantum gravity, might provide a natural cutoff, preventing wavelengths from going to impossibly small sizes and somehow making the process sensible. Others argue that because inflation dilutes everything so tremendously, it also dilutes the memory of those trans-Planckian origins, washing out any observable signature. The final predictions for the cosmic microwave background might be insensitive to what happened at that extreme beginning. Yet the unease remains. If our premier theory for the origin of cosmic structure relies on physics we do not have, it leaves a door open to doubt. The trans-Planckian problem does not disprove inflation, but it highlights its status as an effective theory, a powerful and elegant description of what might have happened, rather than a complete fundamental account. It reminds us that our cosmic origin story is still missing its first page, a page written in the chaotic script of quantum gravity. Our cosmic story may be missing its first page, but what if the final chapter contains a sentence that can erase the entire book? The vacuum of space is not just empty, it is in a state like water can be liquid or ice. and according to our best measurements, it appears to be in a stable, low-energy state, what we call the true vacuum. But there is a terrifying possibility. What if our vacuum is not the true one? What if it is only a false vacuum, a temporary valley in a much larger energy landscape, and a deeper, more stable state lies far below? This is the hypothesis of vacuum decay, and it presents the most absolute end imaginable. Imagine our universe's vacuum state as a marble resting in a small dip on the side of a steep hill. The dip is stable enough, the marble can sit there for billions of years, but it is not at the very bottom. Far down the hill is a deep, vast crater, the true vacuum. The marble in the dip is in a metastable state, a precarious piece. All it would take is a sufficient nudge, a large enough quantum fluctuation, to push that marble over the lip of the dip. Once it goes over, it will roll inexorably down into the deeper crater, releasing a colossal amount of energy in the process. In quantum field theory, this marble is the Higgs field, the field that gives particles their mass. The dip it sits in is determined by the measured mass of the Higgs boson. Our calculations suggest this dip is stable, but the margins are slim. There is a chance, a non-zero probability, that we are not in the deepest valley. If that is the case, then somewhere, at some random point in space, a quantum fluctuation could provide that catastrophic nudge. It would create a tiny bubble, perhaps smaller than a proton, of the true vacuum. The laws of physics inside this bubble would be completely different. The Higgs field would have a different value, which would change the masses of fundamental particles, alter the forces that hold atoms together, and rewrite chemistry itself. But the true horror is not the new laws, it is the bubble's growth. The energy released at the boundary between our false vacuum and the new true vacuum is immense, creating an unimaginable pressure. This causes the bubble's wall to expand outward in all directions at nearly the speed of light. Nothing can outrun it. As it expands, it converts every bit of the old universe it touches into the new reality. Stars, planets, molecules, the very atoms in your body would be unmade and reorganized according to the new alien physics. From our perspective, it would be an end without warning. One moment, the universe is as it always was. The next, an imperceptible point of new law appears and expands to engulf the Earth, the solar system, the galaxy, and eventually everything in a sphere of annihilation that moves at light speed. There would be no flash, no sound, just an instantaneous rewriting of existence. This is not science fiction, but a legitimate, albeit speculative, consequence of our current particle physics models. The universe would not end in fire or ice, but in a silent, perfect correction. It is the ultimate cosmic reset button, triggered by a single, random tremor in the quantum field. And because it expands at light speed, you could never see it coming. The bubble wall would arrive at the same instant as the first evidence of its existence. This leads to a chilling thought. If such an event is possible, why has it not happened in the last 14 billion years? Perhaps our vacuum is truly stable. Or perhaps the quantum fluctuation required is so incredibly rare that the average time we have to wait is longer than the current age of the universe by a factor of billions upon billions. Or, most unsettling of all, perhaps it has already happened somewhere in the vastness of space, and the sphere of true vacuum is on its way, an inevitable wave of oblivion traveling silently through the dark. That silent wave of oblivion is a cosmic end, but the quantum world holds a more intimate mystery, one that asks who or what gets to write reality. At the heart of quantum mechanics lies a puzzle so profound it has split the world of physics for a century, the measurement problem. It begins with the wave function, a mathematical description that encapsulates everything that can be known about a quantum particle, like an electron. This wave function does not tell us where the electron is, but where it might be, a cloud of probability. It can be in a superposition, meaning it exists in multiple possible states or locations at once, like being simultaneously here and there. This is not a lack of knowledge, it is the particle's actual state. Yet when we observe it, when we measure it, that fuzzy cloud of possibilities instantly collapses into a single, definite outcome. The electron is suddenly here, not there. The question is, what causes this collapse and what counts as a measurement? Does it require a conscious observer, a human mind, to crystallize reality from possibility? This idea, while popular in philosophy, is deeply unsettling to most physicists. It places consciousness outside the laws of physics as a magical ingredient that forces the universe to make up its mind. There must be a more physical explanation, one rooted in the fabric of the world itself. This is where the quantum vacuum and its fluctuations re-enter the story through a class of ideas known as objective collapse theories. These theories propose that wave function collapse is not triggered by mysterious observers, but happens spontaneously and randomly due to a fundamental feature of nature. The most developed of these is called continuous spontaneous localization, or CSL. Its proposal is radical. Wave functions are inherently unstable. They have a tiny but non-zero probability of spontaneously collapsing into a definite state all on their own. And the trigger for this spontaneous collapse, according to some versions of the theory, could be the random jitter of spacetime itself, the very quantum fluctuations of the gravitational field or the vacuum. Imagine the wave function of a particle as a delicate soap bubble, hovering and shimmering, representing many possible locations. The constant, minuscule tremors of spacetime foam act like a chaotic breeze. Most of the time, the bubble simply wobbles, but every once in a great while, a specific pattern of these random tremors will hit it just right, causing it to pop, localizing the particle into one spot. For a single electron, this spontaneous collapse would be incredibly rare, perhaps taking billions of years, but for larger objects, the rate of collapse increases dramatically. This is because in CSL, the collapse probability depends on mass or how many particles are entangled together. A dust grain made of trillions of atoms would have its wave function collapse continuously many times per second. A cat or a human is so massive that its wave function is effectively collapsed at all times. This elegantly explains why we never see macroscopic objects like chairs or planets in quantum superpositions. They are constantly being pinned down to a single reality by the relentless background noise of the universe. In this view, the act of measurement is just a special case where a quantum system becomes entangled with a large, macroscopic measuring device, which then undergoes rapid spontaneous collapse due to its size, dragging the tiny particle into a definite state with it. No conscious observer is needed, just the impersonal, random fluctuations woven into the cosmos. The vacuum is not just a sea of particles, it is the ultimate referee, constantly rolling dice to decide which possibilities become real. If objective collapse is true, then the reality you experience right now is not waiting for you to look at it. It is being continuously shaped and solidified by the invisible quantum static of empty space, a cosmic background hum that writes existence one random tick at a time. The random ticks that write reality also seem to write time's story in one direction only. We all feel time's relentless forward march, the unbreakable sequence of cause and effect, the memory of the past but never the future. This is the arrow of time, and its origin is one of the universe's deepest enigmas. The arrow points from order to disorder, from the low entropy past to the high entropy future. But why was the past so ordered to begin with? The answer may once again lie in those first quantum whispers. Recall the second law of thermodynamics, the rule that entropy always increases. It gives us the arrow, but it does not tell us why the universe started with its wind-up key so tightly wound. The Big Bang presented a cosmos in an astonishingly low entropy state, a condition of exquisite delicacy and order that has been unraveling ever since. This is the ultimate unsolved why. How did the universe get wound up? The most compelling clue comes from cosmic inflation. That explosive stretching did more than magnify quantum seeds. It also ironed the universe flat and smooth, creating a vast, uniform expanse with a temperature nearly identical everywhere. This uniformity is itself a form of order, a low-entropy configuration. Before inflation, the universe was tiny, hot, and potentially chaotic. The quantum fluctuations in the inflattened field were random, but the process of inflation itself acted as a cosmic filter. It took those random microscopic tremors and stretched them into the gentle, large-scale density variations we see in the cosmic microwave background. In doing so, it effectively selected a very specific, smooth starting condition for the hot Big Bang that followed. Think of it like shaking a box filled with confetti. The confetti is in a disordered, high-entropy state. Now, imagine the box suddenly expands to the size of a stadium. From your local perspective inside, the confetti around you now appears arranged in a vast, smooth, and orderly sheet, even though the overall disorder of the whole system has actually increased. Inflation did something similar on a cosmic scale. It used quantum randomness to generate a macroscopic state of smoothness, a low-entropy starting point for the classical universe. From that moment on, the arrow was set. Gravity began to work on those tiny density imperfections, pulling matter into galaxies and stars, a process that further increases entropy overall even as it creates local pockets of dazzling order like planets and life. The link is profound. The microscopic, probabilistic fuzz of quantum fluctuations, when stretched across the cosmos by inflation, may have dictated the initial conditions that made time have a direction at all. Our experience of cause preceding effect, of eggs scrambling but never unscrambling, of memories accumulating, might be a direct consequence of a single, random quantum draw in the first fraction of a second. This means the flow of time, the very thing that structures our consciousness and our history, is not a fundamental law written separately. It is an emergent property, a story that began with a quantum tremor in the dark. If the arrow of time was set by a random fluctuation, does that make our past and our future a matter of cosmic chance? If time itself is a story born from chance, then perhaps the stage it plays on is an illusion too. The very space between stars, the gravity that shapes their orbits, might not be the bedrock of reality, but a magnificent mirage. This is the emergent spacetime paradigm, a theory that turns our cosmic intuition inside out. It proposes that spacetime and gravity are not fundamental ingredients written into the universe's first principles. Instead, they are collective phenomena that arise, like temperature or pressure, from something deeper and far stranger, a vast network of entangled quantum bits. Imagine the universe not as a container, but as a cosmic brain. Each individual neuron is simple, firing or not firing, a 1 or a 0. But the connections between them, the intricate web of signals, give rise to something entirely new, consciousness, a rich, continuous experience that cannot be found in any single neuron. In this cosmic view, the fundamental ingredients are like those neurons, simple quantum systems with basic properties, perhaps existing in a realm without any notion of distance or duration. These are the qubits, the quantum bits of information. They do not live in space, they are the things from which space is woven. Their connections, their quantum entanglements, stitch together the fabric of what we perceive as geometry. A strong entanglement between two qubits might translate to them being close together in the emergent space. A weak or non-existent entanglement means they are far apart. In this picture, the three-dimensional, smooth, warping spacetime described by Einstein's general relativity is a statistical average, a large-scale approximation of this frenetic quantum network. It is the ocean that emerges from the chaotic dance of countless molecules. The force of gravity is not a fundamental force pulling objects together, but a thermodynamic force like the pressure in a gas that arises from the system's tendency to maximize its entanglement entropy. It is geometry telling matter how to move, and matter telling geometry how to curve, but all of it is a story told by underlying quantum data. Where do the quantum fluctuations we have been discussing fit into this? They are the noise in the system, the constant jitter at the level of the individual qubits. The gentle, smooth curvature of spacetime on large scales is the average over an astronomical number of these fluctuating connections. The Casimir effect, the subtle pull of the quantum vacuum, would be a microscopic reminder of this underlying churn, a place where the statistical smoothing is not perfect and the granular truth peeks through. Even the fabric of spacetime foam at the Planck scale gets a new interpretation. It is not a breakdown of smooth geometry, but a glimpse of the fundamental network itself, where the individual links and nodes become apparent. This idea finds a powerful anchor in the holographic principle we discussed earlier. The two-dimensional surface that encodes our three-dimensional reality is precisely such a network of entangled qubits. The emergence of the third dimension and of gravity is a direct consequence of the complexity and pattern of those entanglements. So, the quantum fluctuations are not happening in space. They are the primal vibrations of the network, and space itself, with all its stars and galaxies, is the melody that those vibrations compose. This paradigm offers a breathtakingly different answer to the question of what the universe is made of. It is not made of tiny strings or particles in a void. It is made of information and connection. The cosmos is not a thing, but a process, a computation of relationships. And if space-time is an emergent property, then its apparent smoothness is a testament to the sheer number of quantum threads in the tapestry. One loose thread is a quantum fluctuation. A billion threads woven together create the seamless illusion of a continuous reality. If space-time is an emergent tapestry, then the cosmic microwave background is its oldest surviving thread, a fossilized snapshot of the universe's fiery infancy. But what if this fossil contains more than just the seeds of galaxies? Theory 19 suggests it might also hold the imprints of creatures from a far wilder era, particles so massive and exotic they make the Higgs boson seem ordinary. This is the idea of the cosmological collider, and it offers a way to see physics at energies we could never hope to recreate. Our most powerful particle accelerators, like the Large Hadron Collider, smash protons together at velocities approaching the speed of light. The energies released are staggering, allowing us to create and detect particles like the Higgs. But these energies are a flicker compared to the furnace of the early universe, especially during the epoch of cosmic inflation. Inflation stretched space at an exponential rate, and in doing so, it also stretched the wavelengths of any particles that existed back then. This process, incredibly, can preserve information about them. Imagine inflation as the ultimate cosmic freezer. It takes a fleeting, high-energy event and instantly cools it, locking its structure in place before it can decay or change. During inflation, the quantum fluctuations in the inflatoned field were not happening in a silent void. That primordial energy sea could have been populated by other, incredibly heavy fields, particles predicted by theories like string theory or grand unification. These particles would have been far too massive to be produced in any collider we could ever build. Their masses would be near the so-called Planck scale, the energy where gravity becomes as strong as the other forces. But during inflation, the universe itself provided the energy. For a fleeting instant, quantum fluctuations could have borrowed enough energy to briefly bring these gargantuan particles into virtual existence. They would have interacted with the inflatoned field, the very field driving the expansion, and then vanished back into the quantum foam. That brief interaction, however, would have left a subtle fingerprint on the inflatoned fluctuations themselves. It would have slightly altered the pattern of the quantum seeds being stretched across the cosmos. When inflation ended and those seeds became the density variations we see in the cosmic microwave background, the imprint of those heavy particles would have been frozen into the map of the hot and cold spots. It is as if the universe ran its own particle collider experiment in the first fraction of a second, and then printed the results across the entire sky for us to find billions of years later. The signature we would look for is not in the temperature variations themselves, but in their statistics, specifically in a property called non-Gaussianity. The simplest models of inflation predict that the hot and cold spots in the cosmic microwave background should be arranged in a pattern that follows a bell curve, what statisticians call Gaussian. But if heavy particles were interacting during inflation, they would create subtle correlations between spots of different shapes and sizes, a slight deviation from that perfect bell curve. It would be a unique, non-Gaussian signature, a kind of cosmic barcode that physicists could decode to learn the mass and spin of the particle that caused it. Finding such a signature would be a direct window into physics at energies 1 trillion times greater than anything achievable on Earth. It would tell us that the universe's infancy was populated by titans we can only dream of, and that their ghostly influence is still written in the oldest light we can see. The search is on, combing through the exquisitely detailed maps from satellites like Planck, looking for that telltale whisper in the cosmic static. It is a hunt for fossils not of bone, but of force, remnants of a time when the quantum foam was not just the background, but the entire furious story. The hunt for titans in the cosmic static is a search for our deepest origins, but it also forces us to confront a paradox at the edge of oblivion. The very quantum rules that might have seeded our existence could also make the most famous boundary in the cosmos a place of violent contradiction. This is the black hole firewall paradox, and it emerges from a desperate attempt to save quantum information from being lost forever. Recall the classic picture of Hawking radiation. A virtual particle pair pops into existence near the event horizon, one falls in, and its partner escapes, carrying away energy. For a distant observer, this process is gentle and smooth. But if we insist, as quantum mechanics demands, that information cannot be destroyed, then the escaping radiation must be subtly entangled with the particles that fell into the black hole long ago. This creates a problem of fidelity. As the black hole evaporates over eons, the newly emitted Hawking radiation particles must also become entangled with those same interior particles to carry their information out. But here lies the conflict. A fundamental rule of quantum mechanics states that a single quantum bit cannot be perfectly entangled with two separate systems. It is called the monogamy of entanglement. The new radiation cannot be entangled with both the old interior and the partner particle it was just born with. Something has to give. In 2012, a team of physicists led by Ahmed Olmary, Donald Marolf, Joseph Polchinski, and James Sully, often called the AMPS paper, followed this logic to a shocking conclusion. They argued that to preserve the purity of quantum information and avoid a violation of monogamy, the entanglement between the newly born particle pairs must be violently severed right at the event horizon. This severance would release an immense amount of energy. The result, they proposed, is not a smooth, empty space at the horizon, but a blazing curtain of ultra-high energy particles, a literal firewall that would incinerate anything falling in. From the perspective of an astronaut foolish enough to cross the horizon, the journey would not be uneventful and calm, as Einstein's equations suggest. Instead, they would be vaporized in an instant by a wall of fire born from the extreme amplification of quantum fluctuations. This firewall is not a structure made of ordinary matter. It is a manifestation of the quantum field's own internal conflict, a region where the vacuum fluctuations are so stressed by the competing demands of gravity and quantum information that they erupt into a lethal barrier. The paradox is profound because it pits two pillars of physics against each other. General relativity insists that crossing the event horizon should be uneventful for a freely falling observer, a principle known as the equivalence principle. Quantum mechanics, with its ironclad rule of information preservation, seems to demand a fiery death. the existence of a firewall would mean that the event horizon is not just a point of no return, but a place where the laws of physics as we know them break down in a spectacular and violent way. Most physicists see the firewall not as a final answer, but as a signpost that our understanding is incomplete. It highlights the desperate need for a theory of quantum gravity to tell us what truly happens in that extreme realm. Perhaps the entanglement is transferred in more subtle ways through the microscopic wormholes of the ER equals EPR picture, or perhaps our very notion of locality, of events happening at a single point in space, fails utterly at the horizon. The firewall paradox is a scream from the quantum vacuum, a warning that when gravity and quantum information clash, reality itself might have to choose between being smooth and being consistent. And if it must choose, which one would it sacrifice? Firewalls and paradoxes force us to question the very stage of reality, but what if we have been misreading the script from the beginning? What if the most fundamental feature of our experience, time itself, is not a director, but a character that emerges from a timeless script? This brings us to a profound and mind-bending equation that attempts to write the ultimate rulebook for the cosmos, the Wheeler-DeWitt equation. In the 1960s, physicists John Wheeler and Bryce DeWitt attempted a monumental task to apply the principles of quantum mechanics not to particles within the universe, but to the entire universe itself. They sought a wave function of the cosmos. The result was an equation of staggering simplicity and equally staggering implications. At its heart, the Wheeler-DeWitt equation seems to declare something impossible. The total energy of a closed universe is exactly zero. This makes a strange kind of sense. The positive energy of all matter and radiation is perfectly cancelled by the negative gravitational potential energy of all that mass pulling on itself. But the more shocking consequence is that the equation contains no variable for time. The wave function it describes, psi, does not evolve, it does not change. It is a static, frozen object, a single quantum state that encompasses all of reality, past, present, and future, in one timeless snapshot. In this picture, the entire history of the universe, from the Big Bang to the last black hole evaporating, is not a movie playing out frame by frame. It is a single, intricate sculpture. Our relentless experience of time flowing, of moments passing, is an illusion that emerges from within this static whole. How could this be? The key may lie in quantum fluctuations and the concept of decoherence, which we have seen before. Imagine the universal wave function as a vast, complex mountain landscape. Each valley, each peak, represents a possible configuration of the entire cosmos, a snapshot of all particles and fields in a specific arrangement. The Wheeler-DeWitt equation describes this entire frozen landscape. Now we, as complex collections of particles within that landscape, are like hikers traversing a single valley. We do not see the entire mountain range. We only experience the path we are on. As we move, the scenery around us changes. We see rocks, streams, and trees in a sequence. This sequence feels like time. But from a god's eye view outside the mountain, the path is just a line etched into the stone, unchanging and complete. Our conscious experience, with its memories and anticipations, arises from the correlations between different parts of the wave function. We remember the past because our current brain state is quantum entangled with the state of the world that came before it, all part of the same static sculpture. The quantum fluctuations we have discussed, from the primordial seeds to the vacuum's fizz, are not events happening in time. They are features of this timeless landscape, the texture of the sculpture itself. The apparent dynamism, the popping in and out of virtual particles, is just the intricate, probabilistic structure of this single, unchanging quantum state when viewed from within. This perspective turns everything on its head. The arrow of time is not a fundamental law, but a perspective born from our limited, internal view of the cosmic wave function. The universe is not becoming, it simply is. The Wheeler-DeWitt equation is both a triumph and a deep puzzle. It is a landmark step toward quantum gravity, but its elimination of time has been called the problem of time in quantum cosmology. If time is not fundamental, why does it feel so real? The search for answers drives physicists to explore how the familiar, flowing time of general relativity might be recovered as an approximation, an emergent property from this timeless quantum whole. It suggests that at the most fundamental level, the universe may not have a clock. It may just have a shape, and our journey through it is the story we tell ourselves to make sense of that eternal quantum geometry. The timeless sculpture of the Wheeler-DeWitt equation presents a profound conflict with our lived reality. General relativity paints time as a dynamic, flexible dimension, woven into the very fabric of spacetime, capable of stretching and warping. Yet our most serious attempts at quantum gravity suggest time is not in the fundamental equations at all. How can these two truths possibly be reconciled? The answer may lie not in time as a primary ingredient, but as a story that emerges from the collective behavior of countless quantum events, a narrative written by fluctuations themselves. If time is not fundamental, then what we perceive as its relentless forward march must be a kind of statistical illusion, a large-scale consequence of something more basic. This is the problem of time in quantum gravity, and it forces us to ask what creates the arrow if not a master clock. One compelling idea is that time emerges from change, specifically from the correlations between quantum events. In a universe without a global time parameter, individual quantum systems can still interact. The tick of one quantum clock, like the decay of a particle, can be used to measure the sequence of events in another system. Time becomes relational, defined not by an external standard, but by the relative ordering of processes. Your watch does not measure some universal flow. It counts oscillations of atoms, and its reading only has meaning when compared to another process, like the rotation of the Earth or the burning of a candle. Now amplify this to a cosmic scale. In the early universe, the quantum fields were in a highly ordered, low-entropy state, as we have discussed. The subsequent evolution, driven by the laws of quantum mechanics and gravity, involves an astronomical number of quantum fluctuations and interactions. Each interaction creates new correlations and increases the overall quantum entanglement of the universe. Our perception of time flowing forward may be intrinsically linked to this ever-growing complexity of correlations. Think of it like a deck of cards in perfect order. That is the low-entropy past. Shuffling the deck is a process that increases disorder, and each shuffle creates a new, unique configuration. You cannot unshuffle the deck back to its original order without an even more complex series of moves. The sequence of shuffles defines a direction, an arrow. In the cosmos, the quantum fluctuations are the ultimate shufflers. The primordial seeds, the particle decays, the collisions in the vacuum, all these events generate new quantum correlations and increase entanglement entropy. The direction from fewer correlations to more correlations is what we experience as the forward flow of time. From this perspective, the Big Bang was not just a moment of low entropy in terms of matter and energy, but a moment of minimal quantum entanglement. The subsequent 14 billion years have been a story of the universe tangling itself into an infinitely complex web of quantum connections. We, as complex structures within that web, are swept along in this current of increasing correlation. Our memories are records of past correlations, and our anticipation is a projection of how future correlations might form. The quantum fluctuations of the vacuum are not just happening in time. They are the microscopic engines that are generating time's arrow with every random pop and fizzle. They provide the statistical drive, the relentless shuffling that turns order into disorder and creates the irreversible sequence we call history. So the next time you glance at a clock, consider that you are not reading a fundamental dimension of the cosmos. You are witnessing the accumulated effect of an infinity of quantum whispers. each one helping to weave the irreversible tapestry of now from the timeless possibilities of the quantum whole. The timeless arrow we perceive is woven from countless quantum whispers, but those whispers left a distinct signature. Buried within the faint glow of the cosmic microwave background are clues not just to the universe's structure, but to the precise character of its first moment. The pattern of hot and cold spots we observe is not perfectly random. Its subtle deviations from pure randomness, a property called non-Gaussianity, could be the ultimate decoder ring for the universe's explosive birth. Imagine you are listening to static on a radio. True, random white noise has no pattern, no melody. But if you listen very, very closely and you hear the faintest hint of a rhythm, a repeating sequence buried in the hiss, you know that static is not purely random. It contains a signal, a message. The cosmic microwave background is that ancient static, the afterglow of the Big Bang. The tiny temperature variations across the sky are like the volume fluctuations in that hiss. For decades, our best models of inflation predicted these variations should follow a very specific, simple kind of randomness, a bell curve distribution that statisticians call Gaussian. In this picture, the quantum fluctuations that were stretched were simple and featureless, like the bubbles in a glass of soda. But what if the early universe was more like a complex champagne, with bubbles of different sizes and energies interacting as they rose? If the quantum fields that drove inflation were more complex, or if they interacted with other heavy fields during that explosive stretch, they would have created more intricate fluctuations. These interactions would have imprinted specific, non-random correlations into the pattern of the seeds. When inflated to cosmic scales, these correlations would show up in the cosmic microwave background as subtle statistical anomalies, deviations from that perfect bell curve. This is non-Gaussianity. It would manifest as a tendency for hot spots of a certain shape to cluster together, or for cold spots to align in specific, unlikely ways. It is a fingerprint in the oldest light. Finding and decoding this fingerprint is perhaps the most direct test we have for what happened during inflation. Each type of interaction between quantum fields predicts a different, unique pattern of non-Gaussianity. It is like having a suspect's fingerprint on file. By matching the pattern we see in the sky to a theoretical prediction, we could identify the specific model of inflation that birthed our cosmos. Did inflation involve just one simple quantum field or a tapestry of many interacting fields? Were there incredibly heavy particles, relics from a theory of everything, briefly coming to life and affecting the quantum sea? The shape of the non-Gaussian signal could tell us. A detection would be a monumental breakthrough, a direct glimpse into physics at energies 1 trillion times higher than anything our particle colliders can reach. It would move cosmology from inferring the past to reading its detailed journal. So far, our most precise maps from missions like the Planck satellite have found the cosmic microwave background to be astonishingly, almost disappointingly Gaussian. The simple models of inflation remain consistent with the data, but the search continues with ever greater precision because the stakes could not be higher. A single, definitive deviation from that perfect randomness would not just confirm inflation, it would open its engine and show us the moving parts. It would tell us, in the universe's own handwriting, exactly what kind of quantum tremor started it all. That search for a perfect signal in the cosmic static is a quest for our universe's unique fingerprint. But what if our cosmos is not unique at all, but merely one possibility in a near-infinite array, a single tree in a vast forest of mathematical potential? This brings us to the sprawling and controversial realm of string theory, and a powerful new idea that seeks to separate cosmic fantasy from physical fact, the swampland conjectures. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy, strings. The different vibrations of these strings correspond to different particles, like notes on a guitar string producing different sounds. To be mathematically consistent, string theory requires more than the three spatial dimensions we experience. It needs extra dimensions curled up into shapes so small we never perceive them. The specific way these extra dimensions are curled, their geometry and topology, determines the laws of physics in the resulting four-dimensional universe. Things like the strength of gravity, the mass of electrons, and the value of the cosmological constant are all set by this hidden geometry, and here is where the numbers explode. There are perhaps 10 to the 500 or more distinct ways to curl up these extra dimensions. Each way yields a different set of physical laws, a different possible universe. This is the string theory landscape, a cosmic library containing a virtually infinite collection of self-consistent theoretical universes. Our universe, with its specific constants and forces, would be just one volume in this unimaginably vast library. The landscape seemed to offer an elegant, if dizzying, explanation for fine-tuning, like the curiously small value of dark energy. In an infinite landscape, every possible value occurs somewhere. We simply live in a universe where the constants allow for our existence. This is the anthropic principle applied to a multiverse, but a profound question emerged. Is every mathematically consistent set of low-energy physics actually realizable from string theory? Or are some theories, while looking perfectly good on paper, impossible to connect to a consistent theory of quantum gravity? In the last decade, physicists have begun to argue for a striking possibility. They propose that the landscape of consistent string theory vacua is not everything mathematics allows. It is an island or a series of islands surrounded by a vast swampland. The swampland is filled with seemingly sensible effective field theories, descriptions of physics that work well at low energies, but which cannot be completed into a full theory of quantum gravity like string theory. They are dead ends, beautiful maps to places that cannot physically exist. The swampland conjectures are a set of proposed criteria, rules of thumb, that aim to distinguish the landscape from the swampland. They are constraints that any theory claiming to be a consistent theory of quantum gravity must obey, and these constraints have direct, testable consequences for our own universe. One of the most impactful conjectures concerns dark energy, our mysterious cosmological constant. It suggests that in a consistent theory of quantum gravity, dark energy cannot be a true, unchanging constant like Einstein originally envisioned. Instead, it must be dynamic like the quintessence field we discussed earlier. Moreover, its value should not be extremely small and positive for eternity. It should either decay over time or be capable of decaying. A universe with a stable, positive cosmological constant sitting in a perfect, eternal valley might actually reside in the swampland. This directly challenges the simplest and most popular model for dark energy. Another conjecture deals with distances in field space. It suggests that as a field like quintessence evolves, it cannot traverse an arbitrarily large range of values without encountering new, massive particles or a breakdown of the effective description. This places limits on how much dark energy can change and how long acceleration can last. What does this mean for quantum fluctuations? If the swampland criteria are correct, they tell us that the quantum fields driving our cosmos, including those that fluctuated during inflation, are not free to take any value or behave in any way. Their potentials, the hills and valleys of their energy landscapes, are sculpted by the deep requirements of quantum gravity. The random tremors that seeded our galaxies did not happen in an arbitrary mathematical space. They happened on a very specific kind of terrain, one shaped by the hidden architecture of strings and extra dimensions. The fluctuations themselves, therefore, carry information not just about random chance, but about the fundamental boundaries of possible physics. The pursuit of the swampland is a grand exercise in cosmic cartography. It is an attempt to draw the shorelines of reality itself, to say this far and no farther. If these conjectures hold, they would mean our universe is not just any random possibility. It is a possibility that obeys a stricter, deeper set of quantum gravitational laws, laws we are only beginning to decipher. Our search for understanding is not a journey into infinite possibility, but a navigation toward the solid ground of a consistent cosmos. The search for solid ground in a consistent cosmos leads us to a question that has fueled countless stories: the possibility of traveling through time. Could the quantum sea, which seems to permit such wild phenomena as wormholes, also be the very force that forbids them? Stephen Hawking pondered this deeply, and his answer was a bold and fascinating no. He called it the chronology protection conjecture, a proposal that the laws of physics, specifically through quantum effects, actively prevent the creation of time machines to protect the logical order of cause and effect. Hawking was not just being philosophical, he was looking at the hard math of general relativity, which does allow for theoretical structures called closed time-like curves. These are paths through the warped geometry of spacetime that loop back on themselves, allowing an object to return to its own past. They can appear in solutions involving rotating cosmic strings or, most famously, as traversable wormholes stabilized by some exotic form of matter. On paper, these are possible, but Hawking suspected that when quantum mechanics enters the picture, the universe would rebel. His reasoning centered on what would happen in the region where time becomes a loop. Imagine a single photon, a particle of light, traveling along such a closed time-like curve. It could go around the loop once, twice, an infinite number of times. Each time it completes a circuit, it will be present in the same small region of space. In the classical world of smooth physics, this is strange but manageable. But in the quantum world, the vacuum is not empty. It is filled with fluctuating fields. Hawking argued that these quantum fluctuations would also get caught in the time loop. Virtual particles would not just pop in and out once, they would circulate endlessly, their quantum waves building upon themselves with each completion of the loop. This is like the feedback scream you get when a microphone is placed too close to its own speaker. The sound wave goes in, gets amplified, comes out, goes back in, and in an instant the signal builds to a deafening, destructive screech. In the case of a closed time-like curve, the circulating quantum fluctuations would undergo a similar runaway feedback. Their energy would not just add up, it would diverge, skyrocketing toward infinity in a catastrophic buildup. This process, related to what physicists call vacuum polarization, would create an infinite energy density at the heart of the proposed time machine. That infinite energy would warp spacetime so violently that it would destroy the very structure that created the loop in the first place. The wormhole would pinch off, the exotic matter would destabilize, or a singularity would form, rendering time travel impossible before a single paradox could occur. In essence, the quantum foam would become a frothing, furious barrier. Hawking's conjecture suggests that time travel to the past is not merely technologically difficult, it is fundamentally forbidden by a kind of cosmic censorship enacted by quantum physics itself. The universe seems to have a deep preference for a sensible, linear history where causes precede effects. The random, probabilistic nature of the quantum vacuum, which elsewhere creates galaxies and particles, here acts as a universal regulator, a protective mechanism that sabotages any attempt to twist time into a knot. It is as if the fabric of reality has a self-healing property, where any stitch that tries to sew the future to the past is immediately frayed and torn apart by the microscopic turbulence of empty space. So while our equations might allow us to dream of time machines, the silent, seething quantum sea may hold the ultimate veto, ensuring that history remains a story with a single, irreversible direction. The universe seems to guard its past from paradox, but it may still leave subtle, unexplained clues in our own cosmic backyard. Decades ago, as the Pioneer 10 and 11 spacecraft sailed beyond the orbits of the outer planets, scientists tracking their paths noticed something deeply puzzling. The probes were slowing down just a tiny bit more than our models of gravity predicted. This minuscule deceleration, just a fraction of a billionth of the acceleration we feel from Earth's gravity, became known as the Pioneer anomaly. For years, it whispered of a possible revolution. Could it be evidence of dark matter's local tug, a modification to Einstein's laws at great distances, or even a sign of some unknown interaction with the quantum vacuum itself? The anomaly fueled speculation that we were glimpsing new physics, a ghostly hand from the unseen realms gently breaking humanity's first interstellar messengers. Yet, after years of meticulous detective work, the answer proved to be wonderfully mundane yet ingenious. The culprit was heat, but not from any external source. It was the spacecraft's own radioactive power generators, gently glowing with warmth. This thermal radiation, photons carrying momentum, was emitting slightly more from the rear of the craft than the front. It acted like a faint, continuous photon thruster in reverse, providing the exact amount of tiny, constant deceleration to explain the anomaly. A mystery born from the heavens was solved by the simple physics of a warm object in the cold of space. But this story is far from a defeat for discovery. Instead, it sets a breathtaking standard for precision. The Pioneer anomaly shows that we can measure forces so delicate they are comparable to the gentle pressure of sunlight on a sail. It proves our instruments are sensitive enough to detect whispers in the cosmic dark. This precision opens a door to a future where we might detect forces born not from spacecraft heat, but from the vacuum itself. Imagine a future probe engineered to be perfectly balanced, shielded, and cold, traveling into the deep void. Could its ultra-precise trajectory reveal a minuscule push or pull from the quantum sea? Perhaps a subtle signature of the Casimir effect at macroscopic scales, or an interaction with hypothetical dark energy fields. The quantum vacuum is not silent, it hums with potential forces. While the Pioneer's deceleration had a thermal explanation, its legacy is the realization that our technology is approaching the sensitivity needed to listen to that hum directly. The next anomaly we find in the path of a deep space probe might not be so easily explained away by classical physics. It could be the first faint tremor of a quantum fluctuation, measured not in a lab between two plates, but across the vast, empty theater of the solar system. The silence of space may yet hold a quantum murmur, waiting for a quiet enough craft and a precise enough ear to hear it. The dream of infinite power has always danced at the edge of our imagination. What if we could simply plug into the empty space around us and draw from its boundless quantum energy? This is the tantalizing promise of zero-point energy, a concept that fuels countless science fiction visions of limitless, clean power. The logic seems irresistible. We have seen that the vacuum is not empty, but a seething ocean of virtual particles, a quantum foam with a theoretically infinite energy density. It is right there, everywhere, for free. Why not just siphon it off? The answer lies in a fundamental and often misunderstood principle: the vacuum is in equilibrium. Think of it like a perfectly still pond. The water is full of motion, with molecules constantly vibrating and colliding, but on the macroscopic scale, there is no net flow, no current to turn a water wheel. The quantum vacuum is that pond. Its energy is not stored in a usable form like a battery waiting to be tapped. It is the baseline, the lowest possible energy state that quantum fields can have. Those virtual particles popping in and out are not free energy packets you can catch. They are fluctuations around an average of zero. Any attempt to extract energy from this system would be like trying to get a sailboat moving by catching random puffs of air that blow with equal force from every direction at once. The net effect is zero. You cannot get useful work from a system that is already in its ground state, its most stable configuration. To pull energy out, you would need a downhill slope, a place of higher energy for the system to fall from. The quantum vacuum is already at the bottom of the hill. This is the core of the nightmare for engineers. The vacuum's energy, while enormous in theory, is fundamentally unavailable because it is perfectly balanced. It is the ultimate dead battery, yet the dream persists and physics offers a glimmer of possibility, not by mining a static vacuum but by changing it. This is where the dynamic Casimir effect enters the story. Recall the standard Casimir effect, where two stationary plates in a vacuum feel an attractive force due to the restriction of quantum fluctuations between them. Now imagine one of those plates is not stationary. Suppose you could vibrate a mirror or a conductive surface at incredibly high speeds, approaching a significant fraction of the speed of light. According to theory, this violent motion would do something extraordinary. It would disturb the equilibrium of the vacuum around it. The rapidly moving surface would scatter the virtual photons of the quantum field, and some of them would gain energy from the motion, becoming real, detectable photons that fly away. In essence, you are not harvesting pre-existing energy from nothing. You are doing work on the system by moving the mirror, and that mechanical energy is being converted via the strange rules of quantum field theory into real light. It is a form of quantum friction where shaking the vacuum itself makes it glow. The dynamic Casimir effect has been demonstrated in brilliant laboratory experiments using not a physically moving mirror, which is practically impossible at those speeds, but a clever analog. Scientists create a circuit where the electrical properties mimic a mirror moving at near light speed. When they switch this property on and off rapidly, they have indeed detected photons being created from the quantum vacuum, exactly as predicted. This is not free energy, it is a spectacular conversion, proof that a changing boundary can excite the vacuum and produce radiation. So, the zero-point energy dream in its raw, infinite form remains a fantasy, locked away by the equilibrium of the cosmos. But the nightmare contains a secret door. We may never have a zero-point energy reactor in our homes, but by learning to stir the quantum sea in controlled ways, we might unlock new methods of energy conversion and deepen our understanding of the strange substance from which all things emerge. The dream of infinite energy may be locked away, but a more profound treasure might be escaping from black holes all the time: information. For decades, Hawking's paradox presented a stark choice. Either quantum mechanics was wrong and information could be destroyed, or general relativity was wrong and black holes were not truly black. The latest thinking suggests a third path where both theories are right, but our picture of a black hole's surface is incomplete. The event horizon may not be a smooth, featureless membrane after all. New calculations hint that when matter falls into a black hole, it does not simply vanish behind a curtain, leaving behind only mass, charge, and spin. Quantum fluctuations in the fields surrounding the infalling matter could leave behind incredibly subtle imprints on the geometry of the horizon itself. These are not large, classical bumps you could see or touch. They are infinitesimal disturbances in the quantum fields, a kind of faint, ethereal fuzz. Physicists call this idea quantum hair. Just as the unique pattern of your own hair distinguishes you from others, this quantum hair would be a unique signature, a complex pattern of microscopic twists and vibrations encoded in the fabric of the horizon, preserving details about what fell in. Think of it like throwing a book into a pond. The classical three properties, mass, charge, and spin, are like the book's weight, its size, and whether you threw it with a spin. That tells you almost nothing about the story inside, but if the book's impact creates a unique, intricate pattern of ripples across the entire surface of the pond, a pattern so detailed it could theoretically be decoded to reconstruct the book's shape, its binding, even the letters on its pages, that is quantum hair. The event horizon is that pond, and the quantum fields are its water. The infalling matter creates not a splash, but a delicate, holographic ripple in the vacuum fluctuations at the Planck scale. This quantum hair would be woven from the same entanglement connections that stitch spacetime together. So, information is not lost inside the black hole. it is smeared across its two-dimensional surface, stored in the correlations between these quantum hairs. Then, as Hawking radiation slowly evaporates the black hole, this information is not burned away in thermal noise. Instead, the escaping radiation particles are subtly entangled with this intricate horizon pattern. They carry the information out not in their individual energy, but in the complex correlations between them, like individual pixels carrying a hidden image only visible when you see them all together. The radiation would appear random and thermal to a crude detector, but to a hypothetical observer who could collect all of it over the black hole's entire lifetime and analyze the impossibly complex web of quantum correlations, the story of what fell in could, in principle, be read. This resolution elegantly sidesteps the firewall. There is no need for a violent severance of entanglement at the horizon because the entanglement was never purely between particle pairs. It was always a complex, multi-party entanglement involving the horizon's quantum hair and the interior. The paradox dissolves when we realize a black hole is not a simple object with a clean boundary, but the most complex quantum system imaginable, its surface a buzzing hive of information written in the language of quantum fluctuations. If this is true, then black holes are not ultimate erasers. They are the universe's most secure quantum hard drives, and their slow evaporation is not a deletion, but a careful, if chaotic, data retrieval process. Quantum randomness may be the ultimate safeguard against a perfect simulation. If our universe were a vast, deterministic computer program, every event would be a calculation, every choice a pre-rendered outcome. Such a world would feel rigid, predictable, and hollow, lacking the texture of genuine surprise. Yet our reality is saturated with the opposite, with fundamental unpredictability at its very core. This is the strange intersection where physics meets philosophy, where the quantum foam might be hiding the source code of existence itself. The simulation hypothesis, popularized in modern culture, suggests our universe is not the base level of reality, but an artificial construct, a simulation running on some unfathomably advanced computer. For such a simulation to be convincing to its inhabitants, it cannot be perfectly orderly. It must contain elements that feel spontaneous, unplanned, and free. This is where quantum fluctuations become absolutely essential. In a deterministic simulation, true randomness is a problem. Computers, at their heart, operate on logic and algorithms. They can generate pseudo-random numbers, sequences that appear random but are actually the product of a hidden seed number and a complex formula. For most purposes, this is sufficient. But for a universe simulation aiming for perfect authenticity, pseudo-randomness has a fatal flaw. A sufficiently intelligent inhabitant, by discovering the underlying algorithm, could theoretically predict future events, breaking the illusion of an independent reality. The simulation would be cracked. Quantum fluctuations offer a perfect solution to this problem. They are not pseudo-random, they are fundamentally random. According to the standard interpretation of quantum mechanics, there is no hidden variable, no deeper clockwork that determines whether a specific radioactive atom will decay in the next second or a specific photon will take one path over another. The outcome is genuinely probabilistic, a roll of cosmic dice with no prior cause. This intrinsic randomness is uncomputable. No algorithm can predict it because there is nothing to predict, only a probability distribution. For a simulated universe, this feature is a gift. The programmers would not need to invent a flawless random number generator. They could simply build their simulation upon a substrate that has genuine indeterminacy baked into its physics. The quantum noise, the fizzing of the vacuum, becomes the source of the simulation's perceptual noise floor, the static that makes the picture feel real. Every unpredictable event in our world, from the exact path of a lightning bolt to the mutation in a strand of DNA, could trace its lineage back to this programmed randomness. It provides the perfect cover for the simulation's architecture. Even if we, as conscious beings within the program, eventually deduce the laws of physics, we would hit this wall of true randomness and be unable to peer beyond it. The quantum veil would be the simulation's final firewall, protecting the programmers from discovery. This idea turns the purpose of quantum fluctuations on its head. They are not just a quirky feature of microscopic physics, they are the essential ingredient that prevents the universe from feeling like a clockwork prison. They introduce the element of genuine surprise necessary for consciousness to feel free, for history to feel contingent, and for reality to possess depth. The unsettling question then becomes, if our universe is a simulation, is the quantum foam we measure simply the background processing noise of the computer running our reality? Are we, in our quest to understand the vacuum, merely listening to the hum of the machine? That cosmic computer hum may be a fiction, but it points toward a final, breathtaking possibility for the quantum sea. In the universe's last moments, when all stars have burned to ash and black holes have evaporated into faint radiation, the cosmos will be a thin, cold, and nearly featureless expanse expanding into eternal darkness. This is the heat death, the ultimate victory of entropy. Yet one speculative, almost theological theory proposes that even here, at the very edge of nothing, the quantum fluctuations might become the instruments of a final, unimaginable act of creation. This is the Omega Point, a concept developed by physicist Frank Tipler. It begins with a universe that is not expanding forever, but one that will eventually stop and begin to collapse. In this far, far future, perhaps trillions upon trillions of years from now, all matter and energy would be drawn back together in a reverse of the Big Bang, a big crunch. As the universe contracts, its temperature and density rise again. But long before the final singularity, conditions would become extreme in a different way. The background temperature of the cosmos would climb, and the wavelength of the cosmic microwave background radiation would shrink, becoming a source of usable energy. Tipler proposed that an infinitely advanced civilization, surviving in some form from our era, could harness this energy. They would use it to power computers, but not just any computers. These would be ultimate machines, performing an infinite number of logical operations in the finite time remaining before the final collapse. To achieve this infinite computation, they would need a substrate, a fundamental resource that persists even as matter itself breaks down. And that resource, Tipler argued, could be the quantum fluctuations of the vacuum. Even in a contracting, energy-rich universe, the vacuum still fizzes. Those random pops and fizzes represent the last remaining source of true randomness and potential information processing. The civilization could engineer these fluctuations, using them as the fundamental bits for a cosmic-scale computer, a mind that grows in complexity and intelligence as the universe shrinks around it. In this model, consciousness itself becomes the final physical state of the cosmos. As the collapse proceeds, the computational capacity approaches infinity, allowing this ultimate mind to simulate, with perfect fidelity, every possible conscious being that could have ever existed in the history of the universe. It is a form of cosmic resurrection, not by magic, but by infinite computation. Every person, every creature that ever lived could be emulated within this final, transcendent consciousness, experiencing a subjective eternity in the last instant of objective time. The Omega Point is the most speculative idea we have encountered, resting on a chain of immense assumptions, a closed universe, the survival of intelligence across cosmological epochs, and the physical possibility of such infinite computation. Many physicists view it as more philosophy or eschatology than testable science. Yet, it represents a profound and haunting closure to our journey through the quantum sea. It suggests that the same microscopic tremors that seeded the first galaxies could, in the universe's final breath, become the medium for its ultimate self-awareness. From the first random flicker in the inflattened field to the last quantum bit processed before the singularity, the fluctuations are the through line. They are the chaos that gave us structure, the noise that writes reality, and perhaps in the end, the substance from which the cosmos remembers itself. From the first microscopic tremor that grew into a galaxy to the silent wave that could rewrite all of physics, these 30 theories reveal a universe built on a foundation of restless creative chaos. Quantum fluctuations are not a side effect, they are the primal rhythm, the creative and destructive heartbeat of reality itself. They are the sculptor of cosmic structure, the engine of time's arrow, the guardian against paradox, and the potential author of our final fate. The vacuum is not empty, it is the most dynamic thing there is. So we leave you with this question: which of these ideas reshaped your understanding the most? Was it the holographic universe where our 3D reality is a projection from a distant surface, the haunting possibility of the Boltzmann brain, a cosmic accident with false memories? Or the sheer, humbling scale of the vacuum catastrophe, the worst prediction in science? Let us know in the comments below which theory blew your mind. If you want to keep exploring the deepest mysteries of space, time, and existence, make sure to subscribe. We are just